All right, so let us begin our class. I think on the previous day we stopped pretty much here. Okay, so I hope you guys remember that we started to talk about a pretty unusual event um, that stuff has both particle and wave property. And because of the wave property, an electron in a potential well, or when an electron is close to a positive charge, the nucleus, then it does not fall exactly into the nucleus. It stays somewhat away from the nucleus because there is a relation between the energy of the electron and its wavelength. And it can be figured out by following this principle that the kinetic energy is always momentum divided by twice m. And momentum is interestingly related to wavelength, like the following expression: T is equal to h divided by lambda. So using those two expressions, we know that there is a relation between energy and wavelength, which follows like this. Um, energy is equal to h by lambda whole square divided by twice m. And lambda cannot take any arbitrary value. In fact, if you think about a cavity, then the value of lambda is actually fixed and discrete. It can either take this form, or it can either take this form, or it can either take this form, so on and so forth. So because lambda has some finite value and discrete value, energy also has some finite values. Okay, we can write lambda as twice L divided by n, where the value of n is all positive integer, 1, 2, 3, dot, dot, dot. So since lambda has some maximum value, that's why energy, it must have some minimum value. It cannot be zero. And that's why we say that if I take an electron and bring it close to and just uh, drop it into a potential well. Remember, potential well means it's just falling through to the nucleus. So if we drop an electron to the nucleus, it will keep falling down, but at one stage, it won't fall any further because at one particular point, it will reach a minimum energy. Okay. So if you put n equal to 1, you will have the maximum lambda. And for the same maximum lambda, you will have minimum energy. It will not be possible to make energy any less than that. And then we also discussed that since we say that if something can be a particle and the wave, so particle is finite and wave is have some certain spread. So how do we reconcile these two stuffs? If I look at two different positions, will I be able to see both of at both position, will I be able to see the particle or not? And the answer is that we will be able to see the particle with some probability, and we will not be able to see the particle at the same time in all places. For instance, if you look at these waves, these are all different wavelengths, okay? Now, this wavelength, it says that the particle is mostly possible to see at the very center. As you go to the left and right, the probability of seeing the particle would reduce. But let's look at the very other guy. where the waves looks like the following. We take the square of the wave, and this is how we get it. So here, there are at least 4 different positions where the probability of seeing the particle is equal. Okay. Now there are a few more bells and whistles here. And one of the thing is that, okay, I understood that it behaves like a wave. Now, the wave can be eventually the Schrodinger equation. Let me write it here. So from Schrodinger equation, we get the wave function, which looks like the following: a cosine kx plus b sine kx. And we can actually say that if the wave vanishes at 2 different terminal because of infinite potential, let's say this is 0 and this is L, okay? And then we have infinite potential, very, very long potential. So in that case, wave must be 0. And this is the first solution of the wave. So in that case, we can write that at x equal to 0, the value of psi must be 0. So that means if you place this value here, you will see that this guy, A, it also has to be 0 in order to satisfy this condition. On the other hand, if we also know that at a position x equal to L, the wave also is going to be 0. So I have another condition. And from that other condition, we can find out that k is equal to L divided by n pi. Okay. So we know how to find out the value of k. K is the wave number. And we found it out from using the boundary condition. So eventually, if we know the value of k, we can plug back all these values here into the original expression of psi, and we'll get the following. The psi is equal to b sine n pi by L x. That's the solution. So in case of a, if we consider the case of a electron in a potential well, say that the potential well is created by atoms, then what would be the value of L? So let's see. Let us say that we are talking about some crystals. Remember from our very early discussion in the first weeks that crystals are all periodics. Okay, here all the atoms are periodically arranged, and we are interested to know about how electron moves through those crystals. So we go back to that crystal picture, and we draw some periodic nucleus. So each of these nucleus, if you put an electron, let's say close to this guy, then because of the positive charge, this electron is going to be attracted to this guy. But remember that there is also another nucleus here. There is also another nucleus here. And also there's all nucleuses are here, right? So an electron will feel an attraction to both of these guys, right? Both of these guys. So when you draw the potential, then the potential would look like the following. Let's say this is x-axis. On the x-axis, we have all this periodic nucleus. And on the y-axis, we are trying to draw the potential of electrons. So at the very center, the potential would be minimum, right? And as you go outside, as you go more and more further away from the uh, origin, then you will see an increase of potential. So I will draw it like this. Similarly, whenever you reach here, you will see a minimum of potential. As you go away, you will see an increase of potential. So I will draw all the potentials in a periodic manner. All right. So the y-axis is actually the potential energy V, and the x-axis is the space. Let me know if you understand what I drew here. Please, if you do not understand something, immediately stop me, okay? Because in the next time when we'll just develop our idea on top of these things, okay? So in case there is a problem, let me explain one more time. How do I get to this potential? Does anyone remember that how do I know that this is the potential? We discussed about it. There is a way to find out the potential. If you know the force, you can find out the potential, right? How you will find out the force? Well, in case of electron and proton, you will simply use Coulomb's law, right? And from Coulomb's law, so in case of electron and proton, we'll just use Coulomb's law, which says that F equal to electron's charge, proton's charge, or nucleus's charge divided by their distance. And from force, we can find out the corresponding potential energy by simply taking an integral of force. So it will look like the following. Okay. Again, I'm ignoring the sign, positive and negative sign. Just look at the value. So I just drew this guy. Okay. The potential is being drawn here. You see that if let's make it minus. If R is equal to 0, then the potential is going to be negative infinity. And if R is very high, then potential energy would be close to 0. So this is exactly what I drew here. Okay. At the very center, potential energy is very negative. And as you go away from the center, potential energy increases. But again, since there are periodic crystals, so every time you get close to another nucleus, your potential would drop. Okay. So this is why it is all periodic. So the question is, we started to find a solution of Schrodinger equation. We said that psi has some form, and we were able to find out that psi should have the form which looks like b sine n pi by l x. Okay. Remember that previously we have a cosine term, but then we eradicated the cosine term because we said that the wave is going to be 0 outside of the potential well. So the value of L here is actually the distance between the crystal nucleus. So that is L. Okay. Remember that as you try to go outside of this potential, if the potential is very large, then you can say that outside of the potential, your wave is going to be 0. So that's how we know the value of L is actually the crystal parameters. But how about the other parameter B? How we are going to find this out? In order to find it out, we actually use a normalization condition. Let me just write it first, and then I will explain that where does it come from. The normalization condition is psi square is equal to 1. Okay, so if I use this normalization condition, then I will get b square sine square n pi by L x. You take the integration from 0 to L, And then eventually we'll see that B will look like root over twice 2 divided by L. Okay, so how do I know this? How do I know this normalization condition is true? Let me write it here. So this equation is called normalization condition. Okay, and the reason of why it is why the condition came is this, that we're trying to find out the wave of the electrons, but we at least we do not, if we even if we do not know where exactly the electron is, at least we know that if we look out the entire space, at least somewhere there will be electrons. Okay, so if you keep scanning all the space, at some point you will definitely find the electron. So this is why it says that if you scan the value of chi square over all the space, this is actually scanning. Okay, so you are scanning over all the space, then the probability of finding the electron must be unity, must be 1. Okay, so this is how the normalization condition came in, that no matter what, electron must be somewhere. So using this normalization condition, we actually were able to find out all the parameters of the equations. We found out that the value of B must be root over 2 by L. We know that the wave number must be n pi by L. And we also say that L is actually the crystal lattice parameter, like how far all these crystal nucleuses are. Okay, so based on that, you actually get everything that you need to know about electron. All right. Am I going too fast? Okay, sure. Yes. Mhm. Yes. So you're absolutely right that, in fact, it would be the magnitude. In fact, if I try to be more accurate, I should write it in this way. I should write it chi multiplied by asterisk of chi. This is actually the complex conjugate of chi, and together they will become equal to 1 if you take the integral form. So the reason why we do not take the square, instead we take chi multiplied by the conjugate of chi, is the following. So let us say, um, how do I write it? Let us say I talk about a value chi is equal to 2, okay? And I want to take the square of it. Then it's very simple, right? The chi square is just 4. But how about having a chi which is not real, but it could be complex? So let's say chi is equal to 2 e to the power I pi, okay? Remember that this is a complex number. It has both real and imaginary part. The real part would be cosine pi, and the imaginary part would be, do you know what is the imaginary part here? Go ahead, tell me. Right, that's the imaginary part, okay? I'll just put a minus sign here. So since it has both a real and imaginary part, if I have to take a square of it, then I have to take actually the real part, multiply it. I'm sorry, I have to take the value of chi and multiply with the complex conjugate of it. And if I do that, I will get to the square value of it. So when you take a complex conjugate, basically you have to replace the minus I with a plus I, right? So eventually that's how it works, that when you take the chi square, you have to actually take the value of chi and multiply it with the complex conjugate of it to get to the final value of square. Does that answer your question? All right. So before we proceed, let's take a look again into the difference between quantum world and macroscopic world. So I say that in quantum world, um, particle stuffs has both wave and particle property, but in macroscopic world, we do not worry about a wave. We all think about the particle and its mass, momentum, everything. There is nothing about wave when you talk about our body or big stuffs. So how to reconcile these two stuffs? Or in other words, when do we know that we need to take care of wave property and when we can ignore it? The answer is actually here. If you look into the expression of energy, E is equal to nh square divided by twice a square divided by twice m, right? Um, Actually, let me write it here again. So energy is related to nh by twice a whole square divided by twice m. And we said that since, give me 1 second, maybe I missed something here. No, I think I'm fine. All right. So energy is equal to nh divided by twice a whole square divided by twice m. And I say that energy cannot be zero, right? Energy must have some minimum value. Why the minimum value? Because the value of n can be only integer numbers, 1, 2, 3, dot, dot, dot. So if you take n equal to 1, you will see that the energy, the minimum energy is 0. It has the value of h square divided by 4a square divided by twice m, right? That's the minimum energy that a particle has. But if you look into this expression, you will see that you can still have the value of E naught to be very, very small. There are two ways to make the value of E0 to be very small. How we can make E, or if you look into here, there are two ways by which we can make E to be almost zero. How we are going to make it? Even if you take n equal to 1, you can make E equal to 0. How you can do that? Heavy mass, yes. So there are two terms in the denominator. One is m, that is mass, and the other is a. Remember, a is actually the lattice parameter. Okay, I know that previously I used the value of L, but L and A are here as the same stuff. So A is the lattice parameter, and m is the mass of the particle. So if you take a particle which is very heavy, then the value of E is going to be almost vanished. Okay. Now, in order to have a value of E 0, do you have to take a mass which is like a mountain? What do you think? Or what value of M is good enough to almost make E vanish? Go ahead. Say it one more time. Say it loud. I'm sorry. Say it one more time. Right. But what is that value? I know that if M is infinite, then then E must be 0, right? But I'm saying that do I really need to take an infinite mass in order to make energy 0? Or is there some practical value of M which is sufficient to make E 0? Any guess? No? The answer is actually on the top. Look at the numerator. Numerator has a value of h cut square. Okay. So the value of h cut square, what is that value? I'm going to write it here. H cut is actually Planck's constant. And Planck's constant is 10 inverse 34. Okay. So if I take h cut square, what that would be? 10 inverse 68, right? So this means that if you take a mass which is, I don't know, let's say 1 gram, okay? 1 gram mass. So put 1 gram mass into the equation and put the value of h cut into all the equation as well. H cut is 10 inverse 34. So if you plug all these values, you will see the value of energy is just, it's already zero, right? So you really don't need to take a mass which is very heavy. Like even it is a little bit of a particle, immediately you will see the impact of quantum mechanics. You will see that energy is not going to be zero. Okay, so this is why quantum mechanics only becomes relevant. It is true for all of us, even for you, quantum mechanics is true, but its importance becomes very prominent when you go to a very low amount of mass, like an electron. An electron has a mass of 10 inverse 31 kilogram. Okay, it's not 1 gram. An electron has a mass of 10 inverse 31 kilogram. So now we get a mass which is very small. So this is comparable to your Planck's constant. And that's why for electron, these quantum mechanics becomes very important. Understood? All right. So let's see, how much time do you have? Okay, 15 more minutes, right? Please stop me whenever we are on time. So we discussed about uh, what happens when electron is in a infinite periodic potential. Infinite means electron cannot get out of the potential well. Okay, it is always bounded. But in reality, if you take a periodic crystals, periodic arrangement of nucleus, you will see that the potential is actually never infinity. To give you an idea that why potential doesn't go to infinity for a periodic crystal, let me draw you a simple picture. Let's say we are standing on the earth. So this is our earth, the holy mother of earth, and this is you. I know that your potential energy would be minimum zero when you are exactly on the surface of the earth. As I take you outside on the space, your potential energy is going to grow up, right? And we can actually find out what is the potential energy. In order to find the potential energy, we have to again find the force. Force is equal to the multiplication of mass divided by your distance between Earth and you. So the potential energy must be integration of f dx. This is x. So eventually you will get a potential which is look like similar to electron's potential. So I know that the potential would be minimum at the very center of the earth. And then as you go away, the potential it would keep going up, right? So when you reach infinite distance, your potential is also going to be infinite, right? Now let's look at here. Let's say that Earth is not the only stuff in the solar system. There are also other stuff, like there are suns and moons and whatnot. So here we have a moon, right? In the previous case, when we did not consider any other planets except Earth, we know that the farther we go from the Earth, the potential energy is going to go increase. But if we consider the moons and Mars and other planets, do you think that if I take you away from the Earth, your potential energy will just keep going increasing? Yes or no? Let's say you are in the you are somewhere in the center of not middle, but somewhere in between the Earth and the moon. So this means that you are being attracted by moon and also the Earth, right? So because of the attraction of the moon, if you get closer to the moon, your potential energy is also going to decrease, right? So if there was only Earth and nothing else, surely potential energy would keep increasing as you go away from the Earth. But if there are many, many other planets, then potential energy would get smaller as you go closer to other planets. You follow? So in a similar way, in a crystal, since there are all periodic nucleus, the potential energy actually does not become infinite. It actually increases as you go away from one nucleus, but as you get closer to another nucleus, potential energy again decreases. Okay, so this is why I drew this potential energy picture like this. And remember that this maximum value, it never goes to infinite because of the presence of other crystals. Does everyone follow? So if I have um, a periodic potential like this, and if my potential never goes to infinity, then I have some interesting situations. I said earlier that if you have a infinite potential well, then your wave function is all going to be limited between the potential wells, right? Nothing is possible to go outside of the well. But if the potential well is not infinite, then you will see that some wave actually spreads out. So in case of a guitar string, you know that the guitar string always have some specific modes and frequencies. Why? Because at the very terminal, at the very end of the guitar string, you cannot have any wave, right? So this is why all the waves, if you think about this is the guitar string and this is the end of it, then all the strings must have waves like this, right? So this is one mode and this is another mode. You know about it, right? So on and so forth. So this is actually an example of infinite potential well. Infinite means you cannot go outside a certain specific boundary, okay? But if you could go outside, how it would look like? Now, in case of guitar string, you cannot really go outside, but there are other examples where a wave can actually go outside a little bit, okay? An example is actually fiber optic. So in case of fiber optic, if you send light to the fiber optic, you will see that most of the light is going to be confined within the fiber, but some light, a little bit of light, will fuzz out of the waveguide. Okay, I'll show you one picture. Well, this is the video, but I'm not going to play the entire stuff. Just the stuff that I am trying to make. So this guy is trying to make a fiber optic, but in an interesting way. So you see that he actually made a fountain of water, and he's shining light through it. Oh man, you don't see it here? Hmm. How come you don't see it? Okay, there you go. So here, this guy is trying to imitate the principle of fiber optic. Okay. So he took a bucket, filled it up with water, and created a fountain of water through the holes of the bucket. Okay, and he shone a laser light through it. And look at the propagation of light. Not sure if it is very clear from here, but the light is actually bending. Okay, it's bending the way the water is bending. Okay, so water is actually confining the light, and it behaves like a waveguide of light. Okay, so take a closer look at it when you go home. For now, I'll go back to what we are discussing. So we were discussing about the propagation of light and its confinement of light within a fiber optic. So although most of the light is confined within the fiber optic, but if you look closely, for instance, here is an example. Give me 1 second. All right, so if you look here, I'm showing you the cross section of a fiber optic, okay? The circle shows you the outermost boundary of the fiber optic, okay? So if you look closely, most of the light is inside the circle, but some light is going outside, right? Is it visible from here? Some light is going away from the boundary of the circles. So this means that a wave can actually go a little bit away from the boundary, okay? If it is not an infinite potential well, you will see that an electron can also go a little bit away from the boundary, okay? So I think we are up in the time. Oh no, we have a couple of minutes left, right? Okay, so light can go a little bit out of the boundary. In the same way, an electron can also go a little bit out of the boundary. So how do we explain this? The way we explain it is the following. Let me write it here. We started with the Schrodinger equation that says that psi square d square psi dx square plus k square psi is equal to 0. That's Schrodinger equation. We're going to replace k with its particle property, which is twice m by h square divided by e minus v psi is equal to 0. Okay, so k is actually, this guy is actually k. Okay, do you remember that what was k? What was the definition of k? K is the wave number. Okay, so how many waves are there per unit length defines k. Okay, so if something oscillates, not oscillate, if something moves very repeatedly in space, then it will have a higher value of k. Okay, so k is the wave number, and once you get the value of k, we can put that back into the value of psi like this. Psi is equal to b sine kx. Okay, so now here is an interesting thing. K is related to the difference between energy and the potential energy. So remember that E is the total energy and V is the potential energy. Okay, so if K is twice m by h cut E minus V, then K, if energy is greater than the potential energy, then K is of course real. And for the real value of K, we can easily plug that into the expression of psi, and we'll get some other expression. But what if the energy is less than the potential energy? What will happen if energy is less than the potential energy, and when these things can happen. So let's say that we are thinking about these um, crystals, and electrons are somewhere here. As long as electrons are here, we know that the energy is greater than the potential energy. Potential energy is up down here, and energy is up here. But if this electron tries to go here, where the potential energy is actually greater than its actual energy, then in classical sense, this is an impossible situation, because if a particle has a lower energy than the potential energy, it will never be able to go outside of the potential. But if in case of a wave, you can look into the expression of k, and it says that if energy is less than the potential energy, then k must be imaginary. So if energy is less than the potential energy, then k must be imaginary. Okay. So if k is imaginary, you plug back that k into the expression of psi, you will get something like b sine an imaginary value of k multiplied by x. So I understand that if as long as k is real, we can make a sense out of it. But what if k becomes imaginary? That sounds a little perplexing. So actually, imaginary k, have you ever heard of this thing? That sine how do I write it? Let's say sine 20 degree. You all know what is sine 20 degree. But how about sine I 20 degree? I is the complex unit of the complex number. What is this value? Sine I 20 degree? Have you ever seen it? I mean, you don't have to tell it. Even I myself do not know, but have you ever seen it? You seen it? Okay. Yes. So whenever there is a discussion about waves, you will see that these imaginary value is very common to deal with. Okay. Especially the best thing is to just consider exponential. So you know that I'll write it here. So you know that e to the power I theta is equal to cosine theta plus I sine theta, right? Now, what if I write e to the power I theta? I can write it, right? Instead of theta, I can write it I theta. So what will be the result? It will be cosine I theta plus I sine I theta, right? So what is e to the power I theta? It's actually minus e to the power minus theta, right? That's a real value, right? So this means that these guys, they must also have some real values, right? So when you add them together, it will give you a real value. So sine I theta is not an impossible value. This is a true value. Okay. So in next class, we will see that how this idea of in imaginary k or imaginary theta will give us some solutions of electrons when it goes outside of the potential energies. Okay. So for now, let's call it a day. Thank you for your attention. Hope to see you on Monday. And please take a look at the canvas. I'm going to upload some homeworks. Thank you, guys.